Hello and welcome everyone to this PIR live event webinar brought to you by Partners in Research Canada. My name is Stacey Joyce and I will be your host. Remember that you can ask questions anytime by clicking the chat button in the top left-hand corner of your screen if you're joining us live, and make sure you change the to field to everyone so that all of our viewers can see those questions as they come in. And today's guest is Dr. Kathy Tarnai-Lokhorst. She is a mechanical engineering instructor at Camosun College, an adjunct professor at the University of British Columbia, and 30 by 30 champion and counselor with the Association of Professional Engineers and Geoscientists of British Columbia. Lots and lots of words there to describe all that you do, Kathy, but I think there's much more to it. Why don't I let you take it away?
Thank you. Would you like me to start the presentation at this moment or just tell you a bit about me?
Let's go with the presentation, and
Awesome.
If you want to introduce yourself anymore, you can do that as well.
Thank you. So first I have to clarify before I start that I'm not yet a doctor. I'm still working on my PhD. So hope to be soon, but I'm not yet.
Home stretch.
So thank you so much, and I am very excited to be talking today about how engineers and engineering in general works very hard to save the planet. We're around the globe, we're working to make the world a better place. First though, before I can talk about what engineers do, I need to talk a little bit about the difference between engineers and scientists. Engineers are really applied scientists, and so it's important to I think, make a distinction between those two fields. Scientists look very closely at analyzing the detailed specifics, especially the physical scientists. So we're looking for right now, maybe considering chemists. The chemists play with chemicals and they conduct very rigorous experiments to determine how chemicals behave, how they interact when they're mixed, how they produce new chemicals when those mixings occur. Physicists look very closely at the way that light behaves, the way that electricity behaves, the way that forces produce motion, the way that the planets move, the way that the stars are moving in the solar systems. They're conducting their experiments as well in very rigorous, constrained situations so that they can measure each change that they're looking at. Biologists look at the way that our bodies and living beings behave. They look at cell composition and cell structures, how cells mutate and change over time. They look at how different living beings have different cell structures, and they look at the way that our bodies react to other creatures like viruses, and this is an image of a virus, and how our bodies respond to viruses. Again, all of their experiments are done in very controlled situations, meant to be repeatable so that their experiments can be confirmed. What we do then is engineers work very closely with these scientists, and engineers apply that science to result and create amazing things for the world. Sometimes we create things that help scientists do their research, and sometimes we create things that just make life better. It's important too to think not just out of the world kind of activities that engineers do, but we also work on things that are very close to home. For example, some of you may be sitting on chairs that look somewhat like this. Some of you may be sitting on chairs that look like this. They're a little different. They're both made of plastic. They both have metal legs, but they have a different shape. And the plastic is actually different because it needs to carry a different weight of person who's sitting in it. That plastic will have been developed by a chemist, but the application of that plastic will have been created by a chemical engineer and working together with a materials engineer and mechanical engineer to create those processes. Some of you may be sitting in a chair that has a fixed desk. Engineers have worked very closely with teachers to determine what may be a better situation for students in their classroom. Perhaps they want to have a writing surface that's attached to your seat. So that might be the kind of chair that you're sitting on. Or perhaps you have a wooden chair. Some teachers and schools prefer to use wood. Even that wood material has been designed by a materials engineer, and the process for building that chair is mechanical engineering. We work very closely with you to provide drinking water, opportunities. So the bottle itself will be plastic. It's been created by a chemist and manipulated to form a bottle by a chemical engineer and a process engineer. Mechanical engineers may be involved in developing the manufacturing system. So a lot of us will be involved. These bottles recently have come into some negative press because they don't last very long, and so they end up going into landfills, and there are some concerns about bottles that are floating in the ocean. And so material scientists have developed bottles that maybe are the same plastic, but they're better suited perhaps for sporting applications. They're softer and they last longer and can be reused. Or maybe you have a bottle like this one that's a harder plastic, leaches less material, so it's safer for you, but it's not as flexible in case it's dropped at a sporting event. Perhaps you have a metal bottle that's going to last in case something gets dinged against the wall. It's not going to break. These are a lot more expensive, though, to manufacture, and a lot more expensive, too, to put the linings inside them that are necessary to make sure the drinking water continues to be good and safe for you. But they last a lot better than glass bottles, which will break when they're dropped. And so engineers and material scientists and chemical engineers have developed a silicone sleeve that can go around the bottle to keep it better protected. We work closely with athletes. And some of you may have used some sporting equipment that has been modified or improved by engineers. Running shoes are developed by engineers who work very closely with athletes who walk, run, play tennis, or do multiple other activities. If you go to a shoe store, you'll see that the walls for tennis shoes are so great because there's different kinds of shoes for almost every activity that you might be involved in. It's not just shoes and weights, but any kind of sporting equipment has been designed and worked on, improved upon by many engineers who are working to make sporting equipment better for that high performance athlete, or maybe less expensive so that we can get more of these balls into your schools, or maybe stronger so that that hockey stick doesn't break as quickly and lasts longer and your parents don't have to buy so many of them. My son played hockey, so I know what that's like. Sometimes some of you may have injuries and you may have experienced or been exposed to prosthetics. Prosthetic devices like this hand have been developed by engineers working very closely with doctors and other medical clinics to devise prosthetics and artificial limbs like this that are best suited for those people who need them, and be they average people like you and me on the street, or be they high-performance athletes who want to run as fast as they can, or be they our pets and four-legged friends who also lose limbs due to accidents. Engineers work very closely with veterinary clinics and veterinarians to develop prosthetics that best suit those animals' needs. What about electronic devices? I'm sure many of you have used a battery like this, or maybe some of those single flat-celled batteries. Batteries also have been improved upon over the years to make them last longer so that they're less costly and they don't end up having to be thrown away as frequently. Although I hope you're not throwing them away, because batteries should not be thrown in the garbage. They should be recycled. And even this material, then when batteries are recycled, we can reclaim some of the chemicals and the materials and reuse them for alternate uses. Another area where engineers are very busy and hard at work. Other methods of power also are being explored by engineers. Engineers are working really hard to create efficient forms of energy so that we can get rid of using coal-fired plants to produce energy and use some of the clean energy options like hydroelectric dams in British Columbia, nuclear power that's used in Ontario, wind farms that are available across the country, and solar panels that now are coming down in price, and more likely we can use them on our own homes and cars. We don't just work on things that are brand new. Well, and I guess you've seen that with the chairs and bottles. We work to improve things. My area of expertise is working on airplanes. And over the decades, we've been working very hard to reduce the drag on aircraft so that we can extend the flight duration of airplanes using less fuel and having a longer flight so that it takes less time for people to get from the places that they want to be. And engineers continue to work to improve that aerodynamics. And hopefully in the future, we'll see some amazing aircraft that have such low drag that will allow us to fly using small amounts of fuel and maybe even take advantage of suborbital flight to get us from the destinations that we need to get from and to much more easily, quickly, and more efficiently. I hope that I've helped you to see that engineers work very closely to look at the world that we have around us. We meet with many people who have ideas about how to make the world a better place, and our goal is always to reduce the cost, improve, lessen our impact on the environment, make whatever we're providing safe as possible for everybody that we're working with, look for ways to recycle and reuse, and other ways that we can save the planet while keeping people safe and creating better lives for everyone, you, me, creatures, and the world. Thank you.
Well, thank you so much for that presentation. It showed so many different things that I think we can even take for granted on a regular basis that have a lot of thought behind them and a lot of work by engineers and collaborators. So if you want to go ahead and click the stop share button now, we'll see, there we go. We get to see a little bit of a larger picture of you while you answer questions. I was furiously ordering some questions in the background here as they were coming in while you were giving your presentation. So let's start out with a question from Hannah. Hannah is in Toronto, Ontario, and she would like to know, what kinds of people do you work with?
I'm not sure what you mean by what kinds of people.
Maybe are there people other than other engineers, or specific specialty of engineers, other professionals? Who do you collaborate with when you're working on all of these problems?
Hannah, that's a great question. So I am a mechanical engineer, and my expertise is in aircraft design and manufacturing. In working on the airplanes, I worked very closely with other engineers who are experts in their own fields. So people who build buildings, for example, civil engineers, they also work on aircraft, and they do the structural design to make sure that the aircraft are as strong as possible. I also worked with materials engineers and with electrical engineers within the company, and I worked at de Havilland in Toronto, so that was where I had lots of my industry experience. I also worked with flight test engineers and pilots to find out what it was that they were hoping to see in the new airplanes and the new models of aircraft as we were working on designing them. Now I'm working on my Doctor of Social Science, and I hope to finish by the end of the year. And I'm working with school teachers, Physics 11 teachers in particular, to look at ways that we can introduce engineering into the high school curriculum. So that's another way that I'm interacting. In my role as counselor with the Association of Professional Engineers and Geoscientists of British Columbia, I'm working with our local politicians to develop policies that will provide better safety for people in all engineering works.
Very nice.
Question.
I hope so too. Feel free to ask another clarifying question, Hannah, if we didn't quite hit that one on the mark. We've certainly got time to clarify. So that brings us to a question from Ava in Ms. Lazar's grade 5 class. Ava would like to know, what are the different types of engineering?
There are many different types of engineering, and I think I touched on a few of them. So I'm going to use my hand to try and keep track. Mechanical engineers. The big ones are mechanical engineers, civil engineers who, as I mentioned, mostly develop buildings and civil structures. So they will design road systems and urban plans. Electrical engineers will do a lot of the electrical work and design work for everything from those prosthetic devices to the electricity in our homes. Okay, mechanical, civil, electrical. We have biomechanical and biomedical engineers who work closely with the doctors to create biomedical devices. We have materials engineers who will focus on those material designs. We have mining engineers who look at how to best retract and retrieve resources that are in our planet for our use. We have geological engineers who look at the structure of the geology, and they often work very closely with mining engineers to determine what the subground looks like so that they can retrieve those resources. There are software engineers who are designing software systems to run some of our systems and networks, and they work closely with computer engineers who design the computer systems and do some programming as well. There's a lot of overlap between those engineering disciplines. I'm missing some, but it gives you an idea. Really, it's in general, we all apply science. So the discipline decides which aspect of science we choose to apply.
Okay, and that brings me to a question from Kathy Weaver School in Hamilton, Ontario. They would like to know, how long does it take to become an aerospace engineer, and what do you need to take in school to become one?
So working in the aerospace industry requires the minimum of either an engineering degree or an engineering technology diploma, depending on the kind of work that you think you'd like to do. Many of the diploma programs, which are 2 to 2.5 years after grade 12, those will lead into more of the design side of engineering and more of the application. So they'll be doing a lot more hands-on work. If you want to do more project management work, then you would need to have what we call an engineering degree, which is a 4 or 5 year program, depending on the school and depending on if they have work experience. To get into either of these programs, I would recommend that you continue using mathematics right through to grade 12. Doing calculus in grade 12 would be helpful. You'll need in your mathematics to have trigonometry for sure, and lots of understanding of problem solving using algebra would be helpful. The most important thing, though, would be to maintain your physics 11 as a bare minimum. Physics 12 would be recommended. That helps.
Yeah, and I had another question in mind here, trying to string them together a little bit. There are so many. Thank you to our audience for submitting so many great questions. We'll get to as many as we can. And Antigone would like to know, are there some things that aren't fun about being an engineer? Maybe some drawbacks here. We're going to be real. There's drawbacks to everything.
Sometimes, so it depends again on your personality type. For me, I'm a very social person. I like to work with other people. I like to collaborate with other people and work on teams. There are times, though, that I really like to work on my own on a project. And when I'm working and I get my head down and I'm really focusing on something, I don't want to be interrupted. One of my challenges as an engineering educator, I work at the college and the university, is the interruptions that obviously occur on a regular basis from students and faculty, other faculty, as we work together. And so that's why I said it depends on your type. When I'm head down focusing on a project, I don't want to be interrupted, but then I will forget to eat. And when I'm wanting to be collaborating and working with other people, then I don't like to work on my own on some of the details that we need to work on. So sometimes the best part about engineering is knowing that we're working on a team, and quite often we can assign different tasks within the team to the people who are best suited to them.
So on the other hand, Alexandra would like to know, what is your favorite part about being an engineer?
It's problem solving, getting those problems solved, having the solution come at the end and then seeing it come to fruition. As an educator, I'm sure that your teachers will agree that the best part about teaching is seeing that aha moment in our students. When you understand something, suddenly that moment of understanding is just such a joy. And we get that as engineers too, when we're working on a problem, trying to figure out what's the best solution in this case. We had an aircraft, one of the early aircraft tended to fly slightly, just slightly crooked. And so we designed a little lift surface to go up on the horizontal stabilizer in the back. And it enabled the aircraft to fly so smoothly. It was such a simple solution that was then designed through and no longer exists, but on those early aircraft, you'd notice that there's a little extra square of metal on the horizontal stabilizer to provide that solution. And that was from the people on my team.
Very nice. So I bet that was a good day when they tested that one out.
That was a good day. Oh, I have another excellent day when I was working at de Havilland, and I had the opportunity to go on a flight test. When we do flight tests on those early airplanes, they don't have a lot of stuff inside. There's no seats and there's no bins or anything. So I was standing in the opening of the doorway holding on while we were doing our flight. That was so exciting.
And you talked about these moments that are so rewarding in when things go well. You design a solution to the problem, you test it out, it works well, it feels great. Cooper wants to know, if your idea does not work, what makes you want to try again?
Knowing that a solution is possible. Sometimes the best solution is what we call the most elegant solution. It's often the simplest form, and sometimes we don't see it right away. So we'll try something and it doesn't work. I was working on a project last summer trying to figure out ways to use the kind of chemicals to enable greenhouses in British Columbia to maintain and store heat longer. And we were running some experiments and they just weren't producing the numbers that we wanted. But that's part of the fun too, because then we get to sit down as a team and come just brainstorm new ideas. Engineering is very creative. We can look at the issue, the problem at hand, and then just sit around and say, maybe this will work. Maybe that'll work. And then we try them and test them, create prototypes, and see what happens.
So next question is from Ms. Venner's class at Westridge Elementary in Burnaby, BC. They would like to know if you've tackled the problem of drag in an airplane yet, or if that is sort of an ongoing problem that we're looking for a solution to.
It is an ongoing problem. I was saying to Stacy earlier that I had to keep paring out slides from my presentation so that it wasn't going to be a 20-minute slideshow. And in that original show, I was going to show you some of the old early airplanes and the changes that have been made over the years. We're always working to minimize drag. Some of the ways that we do it are ways that now are very common, having flush rivets on the wing surfaces, having very ultra smooth paint that's used on the surfaces. We're changing the way that we design the aircraft. So you'll notice, perhaps if you fly or if you're able to see an airport fairly frequently, you'll notice that on the ends of the wings, we now have these wing tips that come on, and they work really well to artificially extend the length of wings so that we get more lift over that wing surface, and they reduce drag because there's less spillover on the ends. I think that's probably another talk though. So yes, ongoing work, and that's why we keep seeing improvements and changes in the design of aircraft.
So it seems to me then that this isn't really a static problem to be solved in that case, but yet something to improve as much as we can continually. So there must just be ongoing changes in the world of designing aircraft.
Absolutely. We work really hard as well to lighten the aircraft, because if we can make the aircraft lighter, then we don't need as much fuel and we don't need as much lift. So the way that we do that is by changing some of the materials that we use to build the airplane. Early changes were to move from steel structures to aluminum, because aluminum is so much lighter than steel. Now what we're doing is adding a lot of these advanced composite materials like Kevlar and fiberglass that are much lighter even than aluminum. We still use a lot of aluminum though, because it has a lot more strength than those advanced composites in different ways, and it needs to be flexible.
Oh, okay. And Owen at Rolfe Road Public School wants to bring us back to that long list of different subspecialties in engineering. And he would like to know, is there such a thing as a nuclear power engineer?
I believe there is, especially in Ontario, where there's a lot more use of nuclear power. In my day, which is a while ago, it was mechanical engineers who worked with nuclear power, as well as chemical engineers and process engineers. In British Columbia here, we have specializations that really relate to local industry. So we have a lot of work in forest products, agriculture, there's agricultural engineering. We work closely with foresters to develop new uses for forest products and new ways, and foresters are working to manage the forests. So I'm imagining at the universities that are in Ontario, there will be options, at least at the higher levels, to specialize in nuclear power.
Okay, our next question is coming from Madame Serovi's grade 6-7 class in Scarborough, Ontario. They would like to know, what is the hardest thing you worked on?
The hardest thing I worked on? I don't know. I don't find engineering very hard. It's fun. So it's hard for me to think about hard. Perhaps when I was researching new materials, only because it was new to me at the time. We're always learning new things and exploring new things and conducting research to find out what other people have worked on. So I would say perhaps changing modes to learn those new topics, but really it's all been just fun. It's funny to look back. I remember when I was at school, some of the classes I took seemed really hard at the moment. So perhaps it was that learning of brand new things that's the greatest challenge. But then overcoming it, I can look back now and see that it wasn't so hard, more that it seemed to be hard, and I was having a challenge adapting. Not sure. I'm sorry.
I certainly find that myself, that you look back on previous stages in your career, in your schooling, in your life that seemed very difficult at the time, and you overcome that, you master that, you move on to the next challenge, and you look back and you say, well, that wasn't that difficult. Why did I feel like that was difficult at the time? So we're moving on here to a question from Bailey, who would like to know, what is the biggest impact one of your projects has made on the world?
Wow, that's another great question. One of the biggest impacts that one of my projects, well, I would like to think that it's that last project that I'm working on. One of the things that we're trying to do here in British Columbia is extend the growing season for greenhouses, and some of the ideas that we've been exploring are ways to allow greenhouses to hold their heat into the colder months. So we've been looking at using phase change salts, and when materials change phases, they let go of heat. And so the idea is that as these salts solidify, so they go from a liquid to a solid, somewhat like how water goes from liquid water to ice. As they change phase, they hold the temperature at that temperature. So water holds the surrounding ambient temperature at 0 degrees until it all becomes ice. Similarly, these phase change salts will change their phase at higher temperatures and hold ambient temperature at those warmer temperatures. We haven't used these in small and medium-sized greenhouses. Larger greenhouses have a lot of electricity, but these smaller greenhouses are staying off the electrical grid. So we're hoping that we can demonstrate to the farmers that if they simply use these salt packs in their greenhouses, they can extend their growing seasons and provide more food for their local regions.
Very interesting. That sounds like it will have quite the impact, as food security is one of our current challenges to tackle worldwide. So I'd like to ask one more question before we wrap it up today, and that is, if you have any particular advice, nuggets of wisdom, anything like that for our audience today, what would you like them to take away?
Follow your passions. Follow whatever it is that you're interested in, and look for those things that are really easy. When I was young, I always knew what I wanted to be. I always wanted to be a singer. My father said singing was a very challenging career, and it's hard to be a success as a singer, so that I should get a profession first. So I looked at the things that I was easy in, and I always found physics and math fun and easy. So I thought, okay, I'll get an engineering degree. And it's proven to be a joy, absolutely fun. I still sing. I'm still in a band. And I get to have that enjoyment as well as the lifestyle that I can enjoy with having a good professional career.
Very nice. That is unfortunately all the time we have today. Thank you so much, Kathy, for joining us and answering our questions about engineering.
It has been my pleasure. Thank you for inviting me.
Next up on PIR Live event, we are learning about neuroscience and depression for World Health Day. More information on this and other upcoming webinars is available at pirweb.org. Thanks for tuning in, and we'll see you next time. Bye, everyone.